Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're continuing with this LTAM video course, and we're going into Chapter 2, which introduces some basic actuarial notation and introduces the concept of survival models, the survival function, and the hazard function. So, some basic actuarial notation. T sub x is the number of additional years that an X-year-old will live. Notice T sub x is a random variable, depends on the person. Right? It's unknown. K sub x is like T sub x, but it only measures the number of whole years. So, for example, if a given 30-year-old lives to be 89 and a half, T sub x would be, or T sub 30 in that case, would be 59 and a half. K sub 30 would be 59. Okay. Now, if you took exam P, you probably remember some of the basic notation about probability density functions and cumulative distribution functions. That same notation works here too. Little f sub x of t is the probability density function of t sub x, while big F sub x of t is just the cumulative distribution function of t sub x. Exactly what you would expect. What we introduce here that we didn't talk about in exam P at all is big S sub x. That's called the survival function of t sub x. So the cumulative distribution function, big F sub x, is probability of living to some age or less. Survival function is probability of living more than that age. So we get survival function of x equals 1 minus cumulative distribution function of x. Finally, mu sub x is what's called the hazard function, or force of mortality for an X-year-old. That is the instantaneous probability density of imminent death conditioned on your surviving up to that point. So F sub x is probability density of death at some particular point in time, just based on being alive sometime earlier. Mu sub x is probability density of imminent death conditioned on surviving till right up before that. So, for example, suppose we have a uniform distribution of the time of death. Suppose that big T sub 0 of t, the time till death of someone who is just born right now, suppose that's uniformly distributed between 0 and 120. So this person's as likely to have any lifespan as any other between 0 and 120. Find little f sub 40, big F sub 40, big S sub 40, mu sub 40, and then the same for 80. Okay, so we're given that big T is uniformly distributed, and I need to calculate all those other functions. First, it helps to find the survival function of 0, right? S sub 0 of t. The probability that a newborn survives some amount of time. So, knowing what we know about uniform distributions, well, we know that the probability density function is just 1 over 120, where 120 is the width of the interval. Big F sub 0 of t is just the antiderivative of little f sub 0 of t. So you just anti-differentiate 1 over 120, you get t over 120. And big S sub 0 of t is just 1 minus cumulative distribution function, so you get 1 minus t over 120, or 120 minus t all over 120. Okay, simple enough. Now that we have that, we can find S sub x of t, and by extension, F sub x of t, big F sub x of t. For S sub x of t, we're saying of those who survive to age x, how many will survive to age x plus t? Notice that to survive to age x plus t, you must first survive to age x. So that will be S sub 0 of x plus t divided by S sub 0 of x. So algebra happens, we get that S sub 40 is 80 minus t over 80. S sub 80 is 40 minus t over 40. For cumulative distribution function, big F sub x, you just do 1 minus big S sub x To get big F sub 40 of t is t over 80, big F sub 80 of t is t over 40. Okay. Once we have that, for little f sub x, you just take the derivative of big F sub x. So we get little f sub 40 is 1 over 80, and little f sub 80 is 1 over 40, which is exactly what you'd expect for a uniform distribution. If you know that you've lived up to some point, then you only have the remaining portion of the uniform distribution to worry about, and so you just renormalize that and get the new conditional probability density function. The one that isn't quite so easy is mu sub x. In this case, for the uniform distribution, there's a simple kind of geometric formula. Mu sub x is just 1 over the potential years remaining. That once you've survived, say, 80 years, you're going to die at some point in the remaining 40 years, so your probability density of an imminent death is 1 over 40. So you get mu sub 40 is 1 over 80, mu sub 80 is 1 over 40. Okay, what if we didn't have such a nice geometric way of doing it? Well, there's a relationship between the survival function and the hazard function, or the force of mortality. So the hazard function is the instantaneous rate of death, right, the probability density of imminent death, conditioned on not being already dead. And so when we hear instantaneous probability, you can probably do that with some sort of limit, and that's exactly what we do. It's survival at x minus survival a little bit later, divided by the width of the interval, and then also divided by probability of surviving to x to begin with, right? Because we're conditioning on not being already dead. So we get limit as t goes to 0 of s sub x minus, s sub 0 of x minus s sub 0 of x plus t over t, the width of the window, times an s sub 0 of x in the denominator. And if you recognize your limit definition of derivative, that will actually be negative s prime sub 0 of x over s sub 0 of x. And if you're shrewd about this, you realize that this expression here, negative derivative of a function divided by the original, is negative derivative log of the function. And you'll hear me vocalize that quite a bit. Negative derivative log survival. Force of mortality is negative derivative log survival. There's the derivation. You could also invert this to say that survival is e to the negative antiderivative of force of mortality. But we'll deal with that a bit more later. One other formula that I just didn't know where else to put here, but I've got it down here. Probability density is probability of surviving up until that point, and then dying shortly afterward, right? So probability density of dying at some time t, you have to survive until then, and then die. So you get f sub x of t equals s sub x of t times mu sub x plus t. Right? That x plus t is because that is the age you would need to be to die at that particular point in time. Alright. So I should go over some of the properties of what's considered a valid survival function. For one thing, everybody begins alive. S sub 0 of 0 equals 1. Then, everybody eventually dies. S sub 0 of infinity is 0. Now, many mortality models will have some age that you can't live past, just according to the model. We often refer to that number as omega, so we'll say S sub 0 of omega equals 0. And finally, there's the condition that I call the no zombies condition. As far as I know, I'm the only person who works as any form of an educator who actually refers to it that way, but if you call it that, people should be able to figure out what you're talking about. Just that S sub 0 of x is monotonic decreasing. In other words, once you die, you stay that way, so no zombies. Notice that these rules agree with the rules we have for probability density functions and cumulative distribution functions. The cumulative distribution function is an increasing function that goes from 0 to 1. Since the survival function is 1 minus that, it's got to be a decreasing function that goes from 1 to 0. Also, since the survival function is decreasing, its derivative is negative. Its negative derivative must be positive, and since the probability density function is the negative derivative of the survival function, then that forces the probability density function to be positive, which they're always positive, right? They're probabilities. All right. Next, I should talk about some common models for force of mortality. There's uniform mortality. That's the example we just looked at in the previous example problem, where you assume that you're as likely to die on any date as you are on any other. Next, there's you're as likely to die on any date conditioned on surviving to that point. That would be exponential mortality, or sometimes called constant force of mortality. Under exponential mortality, f sub 0 of t equals mu e to the negative mu t, where this mu really is the force of mortality. Notice there's no mu sub x because it's a constant force of mortality. You'll notice that f sub x of t is also mu e to the negative mu t for all x, if you do the algebra on it. If you integrate little f sub 0 of t, you'll get big F sub 0 of t is just 1 minus e to the negative mu t, which gives you survival function of e to the negative mu t. Again, the same for all x. This property that these functions are the same for all x, this is called the memoryless property. And the exponential mortality function is the only continuous function that has that property. Another model for force of mortality is Maxwells Law. According to Maxwells Law, you view it as there being two different ways to die, essentially. One is random accidents, and the other is some sort of biological aging process. For random accidents, it's simple. Random accidents will happen to anybody as much as it'll happen to anyone else, so you just add a constant to the force of mortality. So if we skip to down here, you've got this A out here. That's for accidents. Then, for aging, you assume that every year your likelihood of dying from natural, non-accident causes multiplies by the same amount. So the aging factor, or the aging component, would be this B times C to the X. Every year it multiplies by C. C is usually a little bit more than 1. In a special case where A equals 0, this is called Gompert's Law. So if you see any problems that talk about Gompert's Law, that just means Maxwells Law with A equals 0. And the good news about Maxwells Law is that a lot of the necessary probabilities you have to worry about are actually available in page 6 of the tables that they give you on LTAM. So you don't have to remember too much about it. You just have to remember, you don't even have to remember the force of mortality. They actually give you that as well. But a lot of the algebra is simplified by their, or a lot of the work is simplified by their just giving you the formulas on the table. Now if we compare this theory to contemporary force of mortality in humans in the developed world, here's a graph. Notice it's logarithmic in chance of death, linear in time. That means if Gompert's law were accurate, you should get a linearly increasing function. And you have something that's almost linearly increasing. The two exceptions are for newborn infants, mortality is higher than you would expect. This is sometimes called infant frailty, and sometimes called perinatal mortality, but you have to just remember that really, really, really little kids have higher mortality than you would expect. Then you have this increase from around age 15 till age 25-ish. I've heard this described as the accident bump. I don't like calling it that. To my mind, accidents are the additional A term in Maxwells Law. That's something that will randomly happen to anybody of any age. These aren't accidents. This is recklessness. This is stupid teenagers doing stupid things. So that's what accounts for this bump here. And occasionally, the LTAM will ask something about that, and you'll have to know, mostly linear like this, increase for infant mortality, increase for teenage stupidity. Okay. All right, more actuarial notation. Q sub x is the probability that an X-year-old dies this year. Now, anytime you see a P or a Q, P indicates survival, Q indicates death. So Q sub x is the probability that an X-year-old dies this year. P sub x is the probability that an X-year-old survives this year. If you have this pre-subscript T, which I'll vocalize as TQX, that's the probability that an X-year-old dies within the next T years. And TPX is the probability that an X-year-old survives at least T more years. What about this little vertical line here? That's called a deferred period, or deferral period. I would vocalize this TQX deferred U years. That's the probability that an X-year-old dies in a T-year window, but not the immediate T-year window. A T-year window that starts U years from now. Probability that an X-year-old dies between U and U plus T years from now. And of course, if you replace the Q with a P, then instead of dying in that window, it's not dying in exactly that window. Either dying before, within the next U years, or after, more than U plus T years from now. Okay. Still more notation. Circle E sub x is the average number of additional years that an X-year-old will live. This is called the complete expectation of life for the X-year-old. It's essentially life expectancy minus your current age. Or I guess life expectancy given your current age minus your current age. E sub x without the circle is called the Curtate expectation of life. It's the average number of additional whole years that the X-year-old will live. E sub x is always less than circle E sub x. But not by much, right? It's going to be less by about half. Finally, this half box around the end, that's called angle. Anytime you see this x colon angle n instead of this little x down here, that means instead of saying amount of time until an X-year-old dies, that means until either the X-year-old dies or n years have passed, whichever comes first. And if you want whichever comes second, not whichever comes first, then you would have a bar over the x colon angle n. More on that later. So, as a quick example, what if you're looking for survival probability across multiple years? So if you're given Q sub 60 equals 0.010, Q61 is 0.013, Q62 is 0.017. Given those, find 3p60. Well, you would just have to multiply the probabilities of surviving each year, because to survive 3 years, you have to survive each one individually. Notice you don't have to worry about independence. Typically, if you're multiplying probabilities together, you have to worry about independence. But these survival probabilities are conditioned on your living to that long. And because they're conditional probabilities, you can just multiply them. the whole P A and B equals PA times PB given A. Once it's conditional, you can just multiply. What if for these same probabilities I wanted 2 P60 deferred in 1 year? Well, that would be the probability that a 60-year-old dies between age 61 and 63. So note that would be survival for 1 year minus survival for 3 years. So it would be 0.99 minus 0.99 times 0.987 times 0.983. Crunch the numbers and you get 0.0295. A little less than a 3% chance of dying in that 2-year window. Next, some recursive equations for the Curtate expectation of life. Notice that Curtate, since it looks at whole years, you can look whole year by whole year, which gives you some recursion relations. So, if you're currently X years old, maybe you die this year, in which case of X is 0, or maybe you survive this year, in which case of X is case of X plus 1, right, your survival, plus the 1 additional year you survived, right, between this year and next year. So accounting for both those possibilities, you get 0 times Q sub X plus E sub X plus 1 times P sub X. That's a 1-year recursive equation for Curtate expectation of life. There's also a multi-year recursion, which is a little different. There, you say, well, let me break down the entire future into the next n years and everything that comes after that. So you say, well, on average, how many of the next n years will you survive? That's E sub x colon angle n. Then, if I live longer than that, I have to add in probability of surviving those n years times the conditional expectation of how many further years I would live. Couple loose ends here. There are several ways of calculating life expectancy. Suppose we were given that the survival function for an 80-year-old is 1 over 1600 times t minus 40 squared for t between 0 and 40. By the way, here I'm giving the upper and lower bounds for t. I won't always. If there's something where it's obvious that there are limits to where this function is appropriate, I'll just say, yeah, it should be obvious where it is, but here I did give the limits. So suppose you had to find the complete expectation of life for the 80-year-old. So if you're thinking in terms of exam P, you'd probably say, well, I'd want the probability density. I at least know how to get it, right? It's negative derivative of the survival function. And then I'd integrate t times probability density of t. You could do that. There's a simpler way. What if instead I ask, how many total birthdays will the population have? Well, the number of 81st birthdays you'll have will be S sub 81. Number of 82nd birthdays you'll have will be S sub 82, etc., etc. Then, instead of summing year by year, instead of saying every year, I could say every month, every day, every second. Right? My sum turns into an integral. I just get integral from 0 to 40 of S sub 80 of t dt. And I can get the complete expectation of life that way, by just integrating the survival function. And that's often a simpler approach than taking the negative derivative and multiplying by t and then integrating. Complete expectation of life can be handled with an integral. Curtate expectation of life can be tedious and difficult sometimes. The example we just looked at, the Curtate expectation of life, it's this massive sum of squares over 1600. If you know the formula for the sum of squares, right, n times n plus 1 times 2n plus 1 all over 6, great, you can calculate out, it's 12.8375. But if you didn't happen to know that, this would be a mess. I'll mention there is an approximation technique that I'll talk about in a later video. stay tuned for that. But for now, all you need to know is that e sub x has to be less than circle e sub x, obviously. It's going to be approximately circle e sub x minus a half. And in this case, because the survival function is decreasing concave up, it's always decreasing, but in this case, since it's concave up, that means there are more deaths earlier in the year than later in the year. Because survival function is steeper earlier in the year than later in the year. This means that, so the fact that it's steeper there will force complete expectation of life to be slightly smaller than you would expect, but have no effect on the curtate expectation of life. Therefore, in this case where survival function is concave up, then curtate expectation of life will be slightly more than complete minus a half. If it were concave down, it would be slightly less than complete minus a half. I'll go into how to deal with that concavity in that other video with the approximation technique. I'll get into that. For right now, that's all you need to know. Finally, there is a formula out there that's in the Dixon-Hardy-Waters textbook, so I included it here. It almost never comes up on LTAM, but here it is. Formula for finding standard deviation of t sub x. Well, so I can find the variance and take the square root. This should not be surprising. Take the variance, I can do mean of the square minus square of the mean. That should also not be surprising. The square of the mean, that's the square of complete expectation of life. I just talked about how to do complete expectation of life. We can assume we know how to do that. What's interesting is the expectation of t sub x squared. I could say it's t squared times probability density of time of death. I could also point out that that probability density is negative derivative of survival. And if I integrate by parts, I get negative 2t times s sub x of t, integrated between t equals 0 and t equals omega, where omega is the oldest age you could possibly live to, plus this other integral of 2t times survival. Now, this right here, I said we plug in t equals 0 and t equals omega. At t equals 0, the 2t goes to 0. At t equals omega, the survival goes to 0. So this term just goes away, and I get expectation of t squared is just integral of 2t times s sub x of t. And sometimes that can just be an easier way of getting expectation of t squared. Okay, do that, subtract square of the mean, take the square root, and you've got the standard deviation. Okay, there's the formula. It's in the Dixon-Hardy-Waters textbook. I've almost never seen it come up on anything LTAM related from SOA itself, but here it is. With that, for homework, I'd like you to go through problems 2.1 through 2.8 in the SOA recommended sample multiple choice problem list. Shortly, I will be uploading, chances are by the time you're seeing this, I'll have already uploaded the full solutions to those videos. Again, I recommend work through them on your own, and if you get stuck, then look at the solutions that I present. As always, if you like the way I explain things and wanted to arrange private lessons, click the link in the description below. And until next time, this is Dr. Nighttime wishing you a good night.